Welcome to Dozochem. This video covers precipitation reactions and net ionic equations. I'm going to start with a few reminders about ionic bonding. You might recall this chart that shows you that the column an element is in can give you a clue as to what its charge will be in an ionic compound. So group 1 metals will have a +1 charge. Group 2 or column 2 metals will have a +2 charge. And then we come down here to the bottom. Group 15 nonmetals will have a -3 charge in ionic compounds. Group 16 -2 or 2-, and group 17 1-. And also the aluminum metal cation will always be +3. Transition metals and post-transition metals in the middle of the periodic table can have multiple different positive charges, so they'll specify those charges in Roman numerals. And then there's groups of atoms with charges called polyatomic ions, and here are some common ones that you're likely to see in some of your labs. Now, when you have an ionic compound and you see this symbol AQ after it, they're saying it's dissolved in water to make a solution, and when that happens, the cations and anions are completely separated from each other. So if you ever see the term sodium chloride solution or NaCl aqueous, the metal and the nonmetal actually aren't stuck together in the water. Ions separate completely. The Na pluses and the Cl minuses will be floating separately in the aqueous solution. So a couple more examples: ammonium carbonate solution or NH4,2CO3 aqueous. The ammonium ions and the carbonate ions will be completely separated in the water. By the way, it is true that there's twice as many ammoniums as carbonates, but for now we'll just show which ions are there and not how many. We're not interested at this stage in specifying the number of each, or the relative number of each ion. Last example, iron 2 nitrate solution, or FeNO3,2. We know nitrate has a -1 charge. Therefore, since there's 2 of them, it must mean that the iron has a +2 charge. So it separates into Fe2+ ions and nitrate ions. And again, there are 2 nitrates for every 1 iron or Fe ion, but we don't need to specify that at this stage. So let's talk some terminology. The term precipitate is an insoluble neutral ionic solid formed when the cation from one solution bonds to the anion from another solution. So the question is, when is that going to happen? When are you going to form a precipitate? But let's start by talking about when will a precipitate not form. We're going to use a list of rules called solubility rules. And the one common one that you should probably remember is that group 1 metal cations, such as Li+, Na+, K+ in the first column of the periodic table. This does not include H+, it's not a metal. Ammonium ions, nitrate ions, those ions always form soluble ionic compounds. And what that means is they'll never react to form a solid precipitate in water. They'll just keep floating in the water and not be involved in reactions. So you call them spectator ions. Those are ions that don't react. So we're going to learn how to write an equation called a net ionic equation, and you'll see that spectator ions are ions that don't react. You're going to leave them out. So down here, I've shown the general format of a net ionic equation that leaves out ions that don't react and only includes ions that do react. So what you're basically going to show is which positive ion sticks to which negative ion to form the neutral ionic precipitate. And then the A and the B here are just coefficients used to balance the equation. You basically want the total charge, positive and negative charges, to be equal, so you change the values of A and B to make that happen. So your general strategy is to use the solubility rules on the previous page. The group 1 metal cations, nitrate, and ammonium never form precipitates. And then you'll assume that the other combination does form a precipitate for now. So your goal is to look at the cation from one solution and see if you think it would stick to the anion from the second solution. If the answer is not no, according to your solubility rules, then assume that it does form a precipitate. And then you try the reverse. Will the cation from the second solution stick to the anion from the first solution? And make a decision about whether you think a precipitate will form or not. So here's an example, LiOH aqueous and NiCl2 aqueous. So we're going to look at the positive ion from this solution, Li+, and the negative ion from this solution, Cl-, and see if they'll stick together. But since Li+ is in column 1 or group 1, we know that it can't stick to the chloride. So there'll be no reaction, and Li+ and Cl- will both be spectator ions. Therefore, we will assume that the nickel ion will stick to the hydroxide ion. Now, notice there's two Cl-, so therefore nickel must have a +2 charge. So my net ionic equation is going to show my nickel ion with its +2 charge sticking to hydroxide ions to make a neutral ionic precipitate called NiOH2. That will be a solid. Remember, the ions on the left side will both be aqueous, floating in water, and then they'll stick together to make a solid precipitate. And the last thing you do is put the 2 as a coefficient to represent that there are 2 hydroxides for every 1 nickel ion. So a couple more examples. Solutions of manganese 2 nitrate and a solution of potassium sulfide are mixed. So we want to know, will the potassium ion stick to the nitrate? And the answer is definitely no, because K+ is in group 1, and because nitrate, we know from the solubility rule, will not form a precipitate. So those 2 are going to be spectator ions. Therefore, we're going to assume that the manganese 2 and the sulfide ions will stick together and make a precipitate. So the net ionic equation will be the Mn2+ ion sticking to the sulfide ion. And notice it's not sulfate, which would be SO4 2-, it's sulfide, so it's just the element sulfur, and it's column 16, so it has a 2- charge. The manganese has a 2+ charge because the Roman numeral 2 here tells you that. So the neutral compound formed would be MnS, and that would be your solid on the right side, and then the ions on the left would be aqueous with their correct charges, and in this case you don't have to change any coefficients because the total positive and negative is already equal. Last example, Na3PO4 aqueous and MgBr2 aqueous. So we look and see if Na+ will stick to Br-, and the answer is no, because Na+ is group 1, and that doesn't stick to anything to make a precipitate, so those are going to be spectator ions. Therefore, we assume that the magnesium ions and the phosphate ions will stick together. Mg is column 2, so it's +2 charge. Phosphate, polyatomic ion with a known -3 charge. So in this case, to make a neutral ionic formula, we're going to need 3 magnesium ions and 2 phosphate ions so that the total positive charge equals the total negative charge, +6 and -6 total. And then once you've got the correct neutral ionic formula, you got to come back to the other side and put a 3 in front of the magnesium and 2 in front of the phosphate to balance the equation. Last thing I want to mention is it's possible that neither combination will produce a precipitate based on your solubility rule, in which case there's no net ionic equation or no reaction. So ammonium nitrate plus lithium sulfate, first combination, will NH4+ from one solution stick to SO4 2- from the other solution? The answer is no, because ammonium does not stick to anything according to our solubility rules. So that combination isn't going to work. Then you want to know, will the lithium ion from one solution stick to the nitrate ion from the other solution? And that answer is also no, because lithium's column 1 or group 1, and we also know nitrate will not form a precipitate based on our solubility rules. So in this case, neither combination works, so you wouldn't see a solid form, and therefore you would say no reaction. The solution would look clear, continue to look clear, so there would be no reaction. So that's it for this video. Good luck.